Hello, so I'll continue to talk about ESAIL and mainly about the concept called Multi-Asteroid Touring, which is titled here as Nanospacecraft design, and a bit about the mission, how to do statistical asteroid prospecting. The concept was presented last year here by Pekka Janhunen, and I just give a small update of what we accomplished during last year, small progress about that. There have been involved a lot of people, so which are listed in the last slide, because otherwise I couldn't hit here. So the small facts about asteroids, so about 750,000 known of them, and about 500 billion we know the orbit parameter. This number is constantly increasing due to the observations every day. So with the size, the albedo is slightly more than 100,000 known, and 4,000 with the surface types and the data of the taxonomical class. This number will increase significantly due to next generation of space telescopes such as Sky and Airfleet. And to come to the most interesting bit is how many of those were started. So 20 of them, and just 4 dedicated missions was accomplished, such as Hayabusa or Shoemaker down. Few of them will be explored soon. There's a Hayabusa 2, Sirius Rex, and so on. There are a couple of missions and interest, but each mission cost about $500 million, or in case of research it was over $1 billion, so it depends, so it varies, but the amount of money spent to study one object is quite significant. The Touring, it's become more and more study topic, so there's already a number of satellites that will be launched from NASA, ESA, that will study and few objects with one satellite, because it's bringing more significant data back with the one mission. So there's definitely a big interest. So, but what if you can bring to these things a more statistical approach by the fleet of the small satellites and visit tens and tens of the objects and have a spectral type of those things, which are not visited so far, visit primordial, rapid fires, various sizes and families, active asteroids in the main belt, known and unknown binaries, multiple asteroids system, which are quite of big interest for the mining companies, because about 50% of all asteroids have mini-moons that orbit the asteroid. And the baseline of all of the mining concepts at the moment is to wrap the asteroid, fill up, extract volatiles, and do whatever is done. So you want to find those small objects, and you cannot really observe them from the ground space or in space telescopes, because those could be a few meters in diameter. So those data could be quite valuable for the space mining companies. Potential hazardous asteroids, mapping of migration feature, and selection mapping of potential sample return targets or mining objects in that case. So it was scientific and business cases so called. So with the one launch, you can launch about 50 of them, 50 form a fleet of them. Then you don't need the motherships because of the aforementioned ESAIL concepts that provide you in a sense of unlimited propulsion. And you can visit this perfectly with the one satellite, 2 or 3 objects. But you know, we've been talking all these days about all these showstoppers as the propulsion, communication, navigation, and autonomy. So, and besides of that is the thermal control and radiation, the harsh environment, which is also has to be accomplished. So, the propulsion wise, there is a photonic cell, electric propulsion, has been studied by NASA and ESA, but we already mentioned that was the case over one over R squared in case of photonic cells. So we can't go efficiently so far. We can go to the near Earth asteroids, but with the main belt it's become a bit more complicated. So the electric solar cell indicates approximately 1 over R. So this is the simplified version, as simple as possible. It's a one tether. It's a common system as SQ2 will have, but it will be much longer. It's about 20 kilometers long, and it will spin to maintain the tether stretched. You need this remote unit, the mass, that will keep it stretched. And the center of the mass will be shifted towards the tether away. So they will spin in this way. animation. I don't know if it works. No. Hopefully, it works. It's kind of deploying. I mean, in reality, they'll be farther away, so you spin around the axis, you deploy the remote unit, you deploy the tether, then you perform the flyby, you capture the images, and then you fly back by the Earth, which is not really shown here. Here is a simulation of the flyby from the telescope view. So what you will see is a flyby through the diameter, about 800 meters in diameter, binary asteroid. So you can't really see much. It's dark. I mean, in reality, there's much more object in stars, but just the simulation doesn't have all the data. So in the center of the screen is approaching. Right? It's coming. So you have a distance down there. There's approximately 2,000 kilometers. You start to see it, and then you have a close flyby about 200 kilometers. You capture the data and you fly back. So in close proximity, you spend a few seconds. Because the speed is about 10 kilometers per second. So here's another animation. That's how it will look like. There's Earth's main asteroid belt. Then you deploy this fleet, they will go to the asteroid belt, and then you perform flyby and you download the data for the flyby. So you cancel the need for the permanent communication as long as you have a phone, which is another. So here is the two base concepts and orbit. So you can see the green line here. It's approximately equivalent to 3 AU. So you accelerate for the 1 year, then you tour for the rest of the time. You capture the images, then you perform the flyby by Earth, and you download the images. And another is to Jupiter Trojans, but it's much longer mission, it's much harder. So at the moment, I don't see the possibility to kind of compensate thermally and radiation-wise for this small type of object, because with this baseline, there's a strict requirements for the satellites. So the mission requirements. So you need to mark an escape orbit, then go to your heliocentric orbit with the asteroid belt. The satellites should survive at least 4-year lifetime. Perform 5 wise, 20 or 40 ideally, because of course you will lose probably some of the satellites and some will fail, and you have to also count with that. Let's maximize the number of the flybys, target proximity, and capture images in the visible near infrared and ultraviolet channels. So then you want to maximize the illumination of the surface coverage. Image the whole surface in the low resolution when you far away. In close proximity, you will take the high resolution images and store those data on the flat memories and flyby layers and transmit the data. So with this concept of the one tether, there is 3 requirements. Is the mass for the satellite, and it has to be kept in the range of approximately 6 kilograms. So we are talking something about 3 unit satellite, considering the density. So you can't go much farther with that. The radiation dose is about 100 kilowatt at least, perhaps. And I mean, we know that the radiation will not go as low as at least 10 degrees or something. The storage capacity of approximately 50 gigabytes. So we'll go to the active control, and you need the position and the absolute position there could be probably like under 1,000 kilometers, I believe. And then you can, with relative navigation, more or less try to compensate the distance and come closer to the target. So I already talked about the mission phases before in this animation. So now we come to the satellite. So there's approximately 3 unit satellites. So there is this attitude control module. It consists of the direction wheels and tire propulsion from the to develop in MIT is electrospray, which is quite lightweight, is about 55 grams. Is the propellant, is about 5 grams or something. It has a pretty low thrust, but it's enough for the other kind of just to change the position of the satellite on the telescope. So one. Then there's the main bus, which is based on the S2 bus, which has a bigger battery capacity. And there's this remote unit, which is in case of S2, there was a small mass. Here, so initially, it also was thought to be small mass, but then it ended up with it become bigger and just pile up to the different system. And there's a telescope which takes approximately 1 unit down there, and near the telescope there's a star tracker. So if you go to this remote unit, which initially was the mass, it's ended up to become like small satellite as well, because we realized so actually to do these orbital changes, you need to maintain this spin plane, and for that you need to change the position of this remote unit and compensate this position, and also you want to avoid the spinning around the tether axis because of the damage to the tether. So you need some at least some minimum means of active control, and for that you need since it's stretched, so we assume that the rotation will be just about the axis where the tether is. So for that, for determining position, we need these 4 sun sensors and 4 gyroscopic sensors. Then there's also need this small propulsion, the same as I mentioned before, the style in the bottom, so you have the control around the tether axis. So you can rotate so there's 2 nozzles in the bottom, so you can rotate and then activating by 1 nozzle, but by 2 nozzles you can kind of do changes in this plane by changing the position of the remote unit. So looking inside, so it's become like a small satellite, which is I don't know, what's that size? 0.7 U or something. So it's less than 1 U. It's slightly smaller, but you have to fit it inside the satellite, and it's going to be deployed by the plus bar as the concept at the moment. It's more realistic, which you really can think so. So there's just the stepper motor and this plus bar, and then you just slowly deploy. So because we don't have control over this deployment of this thing, in order to avoid the damage of the tether, because the tether can tolerate up to 9 centimeters, so 9 grams approximately. So the telescope, there was some work done by colleague in MIT, so he's doing this base concept, and so the baseline, the aperture is 17.5 centimeters, and there's a beam splitter that split the signal, so simultaneously you gather the visible and near infrared images, and it was calculated but not tested yet, so in the visible you get the resolution 100 kilometers. So 2 to 5 meters per pixel, and in the infrared channel 5 to 25 meters per pixel. It varies from object and brightness, and the flyby speed as well. So at the moment he's building the engineering model, and he will try to test it and see with the realistic amount of data that we gather. So the mass seems to be possible under 6 kilos. I mean, 5 days with some 20% margin, but there's still thermal control in the common there, so we adopt something that we can still compensate by implementing some other materials. So now we come to temperature. So we started with the remote unit. Okay, you understand that. So cold case. So it's getting really cold. At 3 U, this small body will have almost any active control over it. So we managed to isolate very well the avionics PCB, which is right there. You see the batteries, they get maximum, that's the coldest case possible, this is the worst scenario, so it's get maximum 4 degrees of Celsius. So there's this yellow PCB which is down there, this is its propulsion tile, so cold. So it has the minimum operational range to -10. Celsius can be operated, so it's minus -14. So you can still implement some battery isolation from the rest of the body and keep this temperature higher. So it seems to be realistic, and there's some emissivity in the surfaces and these things. But then we put this thing to the 1 AU, so it's getting really hot. The temperature, which is only 90 degrees, with an outcome and everything. So you have to find the way how to survive with 1 AU and still not freeze at 3 AU, even this small thing. And that's what we are quite challenged at the moment and trying to solve this problem. If some of you have some suggestions or some good ideas, I already gathered some yesterday. Nice dinner, but would be really nice. The radiation load is also on the match, so we have 1 millimeter max of aluminium. However, probably some for you it won't be surprised, but I was quite surprised. I found this article where it claims that actually carbon fiber has much better radiation shielding than the aluminium. So as the proton bombardment at 10 mega electron volt, so it has about almost like 50% better shielding capabilities. I mean, it's obviously not used in low Earth orbit due to the atomic oxygen erosion and stuff, but in interplanetary space, it can be somehow compensated to reduce some of the masses. So the conclusion: so fly by hundreds of asteroids, enabled by electric solar wind sail. It needs the full trajectory analysis, and it has a minimal use of deep space network, just some use for the communication. It needs the optical navigation and spatial autonomy, and the instrumentation. I mean, it was involved by the space lab and so on. So such instruments are used for the Earth observations. So yes, it has a preliminary study at CubeSat, but it was not performed yet. The full range study. Oh yeah, and fly early and fly often. So that's why the SQ in development and some other satellites. So try to maximize those things. Because all the people who was involved in this project and contributed scientifically or engineering wise, and this list probably expands every day more and more. Thank you for your attention. Perhaps run out of time, so.
Okay, just to come back on the maneuvering of your essay, is it not possible to actually not have a constant current going on in your tether for the world rotation? For example, if you put the currents, I think it's going to be the idea that you had before. If you put the current only on half of the rotation, you will induce torque on your essay.
Yes, definitely, yes.
So, and yes. Then you will not consume any air and you will extend your lifetime.
Yes, but you still need. I don't remember. There was definitely a reason why it was necessary there. I mean, anyway, you can regulate voltage and you can switch off the voltage fully. So you lose the trust at some because the spin part is quite slow. So it's about 2 rotations per minute, I believe, something like that. So you can switch on the voltage in one side and then another one. But there's definitely I can't recall now that there was a few issues that were required actually this remote unit to be controlled. At least at some points.
Yeah, could you say something about how you navigate one of these tethers to a flyby? Because the solar wind velocity and therefore the thrust you get varies day to day potentially by factors of 2. So you have a highly non-deterministic component to the acceleration you get. How do you know you're going to get where you're going? Do you miss an asteroid if you end up in a slow solar wind stream for an extra week?
You probably can know this when you lose a satellite, perhaps. Maybe it happened for a really long time, and this acceleration will be much lower than was expected. But I don't have an answer for that. But it's a very good question.
To comment also, as you, Iaroslav, already mentioned, that this voltage can be scaled. So the voltage of the tether can be anything from 0 to 100%. So this thrust that you obtain from the solar wind can be tuned. So
but you have to actively control it.
At least that's possible.
I wanted to ask you how well can you maneuver also the spin orientation and the plane? Because I guess you need to have the object inside of the field of view with a very short approach and maybe some inertia to control this.
Yeah, I mean, you can control it quite well. I think in 3,000 kilometers approximately, you spend about 10 minutes, so you still have some time to correlate it. I don't know how fast you can actually change this plane radically, but I think actually that was one of the reasons to have this propulsion and then the tether, so to change this plane in quite short time. So.
I think it's very similar. you probably need to change the spin plane, the rotation axis, let's say, and then how much does it cost to change, to tranquilize again, to come back? So how much does it cost in terms of time, in terms of propellant? Each time you want to
change the entire plane of the rotation.
yes. If you need, and I think we
Yeah, perhaps yes. I mean, of course,
okay.
Unfortunately, I did
It has to be assessed.
calculated
Yeah.
and simulated. I don't have an answer.
Okay.
Here. Okay. So you have a spectrometer and
No, it's not the spectrum. We don't have a power for that. So it's just it's the images just taken in different channels. So you have a filter array. So you have a filter array with different filters. It's a narrow band with just one channel, and then you turn the reel, and then you take the multiple images with different spectral types. So it's in the spectrum. I'm sorry.
no, it's okay. That was my mistake. But I see a very high resolution, probably better than what can be achieved currently in LEO. So I was just wondering what the size of this camera is.
So it's 1 unit.
The whole unit. Okay, yes. Okay, thank you very much. Well, very nice presentation, by the way.